Today topic is an ADC. So an ADC is analog to digital conversion. The main objective of this ADC is to convert analog signal into digital signal. We already know that the IC process only binary data. So in order to store the data, we need digital data. So in the real world signals are analog signals. We cannot process that analog signal directly to the IC. That's why we are going for analog to digital conversion. In ADC, we have four types of ADC. One is successive approximation. Second one is single slope DAC and ADC. And the third one is a flash type ADC and a dual flash ADC. So these are the techniques that's available in the ADC. Among that, successive approximation play a major role. So this is a general block diagram of an ADC. So in this ADC, it consists of comparator, logic control, successive approximation register, 8-bit, and DAC, digital to analog converter. So in order to perform this successive approximation, we need three clock signals. One is input clock, it's an asynchronous event. Okay, that's a stable multiplier from the circuit, will giving the clock signal. Then two process, start of conversion, another one is end of conversion. So in order to control this successive approximation, we prefer these two signals. So here we are giving the input signal, that is analog signal, that will be performed by sampling, holding, truncation and round off. That data will be given to the comparator. So the main objective of this comparator is to compare two signals. So we have given to non-inverting terminal. So this is non-inverting, it's an inverting terminal. For inverting, we are taking the output from DAC. We will set the reference value. For example, just imagine input voltage is 5. I am setting the reference voltage of plus or minus 2.5 volts. Plus or minus, I am setting 2.5 volts. What the comparator will do? It compares two signals. Okay, that's a condition, as I emphasized earlier. So this is a VA and VD. So here we can write VA is greater than VD, means the output will be 1. And VA is less than VD, output will be 0. So here the comparator compares two signals. Based on the value, it sent to the logic control. So it's similar to a buffer, it stores only 1 bit at a time. The data will be sent to the SAR. So SAR is nothing but successive approximation register. It holds 8-bit data. 8-bit data. There are a number of ADC types. Here we are using only 8-bit ADC. Okay, 2 to the power of n. So this section is an output. Okay, it will be compare successive approximation register with the DAC, and the data will be taken from the between SAR and DAC. So we are going to compare applied input and converted output. Okay. Here we are applying analog signal. That analog signal is converted to digital signal. That signal has to be compared with binary and digital signal. Okay. So this is a binary and digital signal. So this is an analog signal. Okay. This signal we have to compare with this and we have to find out the value. So that's what we are using with the help of this table. Okay. So initially the data will be starting from LSB and end with MSB. Least significant bit, most significant bit. Why I am using 8-bit means this ADC contains 8-bit register. That's why I am preferring 8-bit. Okay. So these are the output I am going to be verifying. For example, first condition D0 I am getting 0. So here 0 means here I am applying reference voltage is 0. Now whatever the signal you are getting, output will be 1. Okay. So the output of the comparator will be 1, output voltage will be 0. So this comparator output fed to this MSB. Okay. Then we take value 128 volt. Next, here the last comparator bit is 1. That will be added. So it will be shifted. Okay. This will be 1 and last one will be 2. Now we are taking the value 128, 64. We are getting 192. So the value is less. This value is less when compared to 212. Okay. This is a 212 volt. So again I am comparing and getting the comparator output 1. Next condition, this 1 shift here. So here the condition this test. So in this case I am getting the value greater than 212, 224. So this value is higher value. Okay. The VD value is higher value. So VD value is higher value, the compared output will be 0. So I am getting the compared output will be 0. So I am taking that 0. For example, this bit I am taking here. I am adding 0. Then these 2 bits as it is. Okay. If I shift these 2 bits here now, the value will be less. I cannot get this output. Now to obtain the output, I am taking. For example, you take 0 or 1. You take 4 combinations 0, 0, 0, 1, 1, 0, 1, 1. If you are taking D0 to D17, how much value you will get? Up to 128 values, you have to keep on searching, take time. Not to minimize that, for our assumption, we are performing this. Okay. Next condition, we are taking the same value, the output is 0 here, and previous this one will be close here, and this one, that is added 1. Here also 0, we are again comparing, that's 216. 216 is compared with 212, so this value is very high. Okay, so that's why the name successive approximate. I am approximately varying this value and I am checking. Otherwise, sequentially, I have to check up to 128 sequence. Up to 128 sequence, I have to check. Not to minimize that, I am using certain technique to compare the sequence. Okay. So earlier I emphasized, in order to obtain 212, you have to convert to binary number. If you convert it, you can easily 2 or 3 steps you can take an output very easy. So that's why they ask you to find out the value of 212. So here you will get 212. So these 2 values match, so you can get an output. So based on these binary numbers, you take an output. Okay. For example, if you apply 212 analog voltage, here I am getting the MSB bit here 1 1 0 1 0 1 0